So good morning, everyone. So we continue with the fluid statics, and then we move on to fluid dynamics today. Some part fluid statics. So yesterday we dealt with cases when liquid was unaccelerated. What happens if liquid in a container is given a horizontal acceleration? That's what we were discussing yesterday. And most cases, fluid statics is application of laws of motion. So here also, if you imagine, if a part of a liquid which is a cuboid, if I take that as a system, so every particle in the liquid will have same acceleration A in the horizontal direction. If I take this as a system and mark all the forces, including the contact forces, I come to understanding, I come to this expression that when liquid is accelerated, so there has to be net force acting towards right. That's why then only the all liquid particles will get accelerated. And net force towards right will act because of difference in pressure on left face and the right face. So this face has to have higher pressure compared to face on the right. So if a liquid has this kind of acceleration, if I take a horizontal surface, unaccelerated liquid, horizontal surface pressure remains constant here. Here the pressure will keep increasing which direction? Opposite to direction of acceleration. And rate of change of pressure, rate at which pressure will increase, dp by dx is equal to minus rho into a. It's very similar to dp by dh is equal to rho into g, something similar. Okay, so that's what happens. And how does extra pressure come? Pressure at this point is more, the pressure at this point has to be equal to, if I take the word, this is the liquid here. So if there's a pressure is atmospheric here, if I take gauge pressure, the gauge pressure at this point has to be equal to rho g into height about this point. So if left hand side pressure is more, the height of the liquid also has to be more compared to right hand side. So what is the slope? Slope comes to equal to, slope is a dimensionless quantity. So it is one form of acceleration divided by other form of acceleration minus a into g. Negative sign because if acceleration is towards right, it will have negative slope. So this is the two things we need to understand here in case of horizontally accelerated fluid. There are three things if I say. Laws of motion, if we take any system of some volume of liquid or some mass of liquid, net force must be acting towards right. If net force is acting towards right, the pressure towards right is greater. And the pressure is greater, that's why there's a pressure gradient here. And pressure gradient is equal to dp by ds minus rho into a. And pressure gradient is on account of, if it is exposed to air like this, the pressure difference is because of height of difference in height of liquid above that point. And that's why it takes a slope here. So pressure increases against the direction of horizontal acceleration, similar to vertical acceleration. So dp, change in pressure between 2 points, if we take 2 points separated by distance x. See, in vertical direction, we calculate delta p as density. So notice the similarities are rho g delta. This is what we do in case of vertical acceleration. So very similar in horizontal acceleration. Horizontal direction density remains same. Horizontal acceleration into delta x. This is distance measured along horizontal axis. So let's take up a couple of cases here. YouTube is filled with the same volume. So we have two liquids filled here. One is of density, so has base length of L. So this length is L here. It is filled with same volume of two liquids, density rho and 2 rho, and is moving in the acceleration A towards this right hand side. So, and what we find here, one of them have a density of 2 rho and other liquid has a density of rho. So two densities, they are not equal, but for a particular acceleration, what we find, these levels on both sides are equal. So this level and this level, both sides are equal. Based on the information, can we find out which density is which liquid is having higher density? The one in the black or one which is hatched here? Which will have higher density? How do I think which will have higher density? So the one which will have higher density, I have to think now, if I take this point as A and this point as B, which point will the pressure be more? They are lying in the horizontal plane. But one of them has higher pressure, because horizontal plane also, because of horizontal acceleration, pressure will not be equal. Which one will have higher pressure? A will have higher pressure, pressure increases. So what is be PA minus PB equal to? So if I have to calculate as A will have higher pressure, and since the pressure at A, so first thing what you understand here, one by one we analyze here, pressure at A has to be greater than pressure at B. And what is pressure at A equal to? Pressure at A equal to if rho1 into GH, and that has to be equal to, if I call this density as rho2, this is equal to rho2 into GH. Heights are same. So this clearly indicates that this liquid has to have higher density. This has to be equal to 2 rho, and this has to be rho. Then only it is possible. Now let's again examine here, and if I have to find out PA minus PB along horizontal direction. See, when I apply, how do I calculate change in pressure in horizontal direction, delta P? Change in pressure in horizontal direction is equal to something similar to, in case of vertical direction, is rho G delta H. This also is similar. This is equal to rho into A into delta X. So rate, but the change in pressure depends on density here. So if I want to calculate difference in pressure between A and B, so when I look at this from A to this point here, there's one liquid, and from here to here, there's another liquid. So let me call point this is C here. So I can calculate pressure difference between PC minus PB. Because between C and B, there's the same liquid which has a density of rho. So PC minus PB, which is higher? C is higher. PC is higher by how much? Is equal to density of the liquid between those 2 points into acceleration and this delta X here. So total length is L, and since volumes are equal, this length has to be equal to L by 2. That is PC minus PB. This one equation you can form. And similarly, if I take pressure difference between points C and A, which will be higher against the pressure, so P will be higher. So PA minus PC will be equal to 2 rho now into A into L by 2. So this equation I have to find. If I subtract second equation, if I add a second equation and first equation, I get PA minus PB. So PA minus PB, pressure difference between A and B, has to be equal to, it comes equal to rho AL by 2 plus rho AL, which is equal to 3 by 2 rho AL. Okay. So this is the pressure difference between the two. And if I calculate pressure difference, I have calculated along horizontal direction. I could have also calculated pressure at A and B separately vertically. If I write that equation, PA will be equal to how much? PA will be equal to 2 rho GH, and PB will be equal to rho GH. So what is PA minus PB? So PA minus PB is equal to rho GH. So this is first equation I arrived at based on calculating pressure difference in horizontal direction. This I have calculated in the vertical direction. Both, whichever we calculate, both have to be equal. So if I calculate, I get rho GH has to be equal to 3 by 2 rho AL. So if I have to find what is the acceleration I must give so that both have equal column height, this is the equation. So this equation we arrive at, and this is step A, Salah.
Sir, how is PA and PB not affected by A, sir?
How are they then? Not?
Affected by the horizontal acceleration.
They, are they not affected? They are affected. That's why the pressure at A and B are not equal. Where did I say they are not affected? So had the acceleration been not there, see, would you have got same expression if the acceleration was not there? Think of it. If density is more, do you think this both column would have come to the same level, LR? What would happen if this density is more? What would happen? Tell me. See, if a horizontal acceleration was not given, see, if I pour this liquid and assume that there's a kind of stopper here. So when I stopper here, I can fill up this liquid on one liquid on one side, other liquid on the other side. And if this density is higher density and this is lower density, as soon as you open the boundary here, what would happen? This density being more, this would have level would have dropped here, and this level would have risen. This level on two sides cannot have been equal. They become equal because of horizontal acceleration. So there's an effect of acceleration. It's only that you just see that what is the effect of acceleration. And that's why I calculated pressure at A and B are not equal. They are different. So any part of liquid here, see, if I accelerate here, if I take a small mass here, is this mass experiencing any net force? Of course, it has to experience a net force equal to ma. Which direction? This direction. How does this net force comes? Because pressure acting on his left hand side is greater than pressure force acting on the right hand side. Ahlad, is that clear now?
So like we're calculating pressure, we need to take only one of the applications.
We have to take. No, I
Like
am not calculating pressure. So basically, to calculate pressure, I have to start with a known point, and I am calculating difference in pressure. How is the pressure changing in horizontal direction? How is the pressure changing in the vertical direction? That's what I'm doing here. Is that not?
yes, sir.
No, so that's what we do. And so, anybody has any other question?
Sir,
Yes.
so they said the both the like liquids are of same volume. That's why we know the bottom one is L
Yes.
by 2 and L by 2,
Yes.
right?
That's why L by 2. Otherwise, very good. Otherwise, it would not be L by 2. Yes. So we understood. I would have given the question in other fashion also. See, suppose we put a stopper. Have you understood what I said if we put a stopper here? Is this point understood? Abhiru?
Yes, sir, it cannot rise above that level.
So basically, but moment I open the stopper, unless if I don't give an acceleration, what would happen? This interface, the boundary would have moved. And we had done a similar question yesterday in case of vertical circular ring. And so what happens if this is open, if this can move, and this level would have come down and this level would have risen, and we can calculate also. If this value is given here, what would be the level difference if we stop this? Suppose we slowly make A is equal to 0. What will happen? It will not remain in the same shape. Assume that pipe continues here, the level difference will come, and we can easily calculate what the level difference would be. Yes, that also can be calculated, and someone can easily try. That's a very simple question to solve. Okay. Now move on to next one. So I think perhaps maybe I could have taken this question first here. There's a beaker containing liquid of density rho. So this is something you can examine, and every time whenever question is given like this, is accelerated forward with a constant acceleration E naught. If you suddenly accelerate, the whole thing will start oscillating. So every time we have to assume this acceleration is given is slowly increased so that the liquid level also changes in such a slow fashion that it is not jumping up and down. So it is acceleration gradually it has increased to A naught. And I find in that state, it is in a steady state. The steady state with this acceleration is constant, and liquid level also makes a particular value of slope here. And it will be a particular slope. And what would be the tan theta be? This is what we have done. Tan theta and that is slope will be equal to minus A naught by G. The minus sign indicates negative slope. So that's how, and we can that I think it makes intuitive sense also. There's one more way we could have calculated this. We could have arrived at one more way. I think maybe I'll tell the next session if some of you are interested. So in this case, what we need to do, we need to find the pressure difference between point 2 and 1. What is the pressure difference between point 1 and point 2? So here also, just see that one. I'm just doing this slightly different way. Let's do different question different way. So I write to start from here. Let the pressure at point A is P1. This point is pressure is P1. So let me, this point is 2, and let me point in between point this, let me point this point P here. To calculate pressure difference, I will measure this, let me take process P1. I will only write change in pressure. So as I move from 1 to P in the same horizontal direction. So same horizontal direction, the pressure will change only about A naught. It will not change because of G. So what is, and we are moving against the direction of acceleration, the pressure will increase. So from compared to 1, the pressure at P, if I have to write one more step, pressure at P will be, which is at the same level as point 1, will be equal to pressure at 1 plus rho and A naught into L. That's what I written. So compared to 1, it will be increase of rho density into acceleration A naught into delta x, which is L. And from here, as I go up in upward direction, now I'm moving in the vertical direction. The vertical direction, horizontal acceleration will not have any effect. The pressure will decrease in vertical direction by how much? Rho into G into vertical height. So it will decrease by minus rho GH, and that will be equal to P2. So that is something similar to what we do in case of Kirchhoff rule. Very similar and starting point. There also we track potential. Here also we are tracking pressure. Very similar way, and this is how we can find. And this expression we come to in case of horizontal acceleration plus vertical acceleration. So it's a very simple application of change in pressure due to horizontal acceleration, which is equal to minus, similar to rho GH, it is equal to rho into A into delta X. Okay, and this is a open cubical tank. So this height is L, base is L. It's a cubical tank, and other dimension which is perpendicular to plane of the figure, that also is L. So what is given? This tank was initially filled with water. when the tank was accelerated on horizontal plane along one of the side, it is found that 1/3 of the volume of water has spilled out. What is the acceleration? And this also makes sense. When you have acceleration, what will happen? What? See, if earlier it was filled here, as we accelerate, let's say this something, see, if the whole thing was, as it will take a slope, the water will spill out from here. Some water will spill out because the slope has to match here. The liquid will always take a slope which matches with this equation in a steady state. This tangent theta has to be equal to minus A by G. Okay, and only way it can have this slope is by this point has to be the highest point. The liquid will tend to get pushed backward, so it will spill over from this side. So if this state 1/3 is filled up, so this height will remain h here. Let this height be h here. So I don't know what this height is h here, but what is given the remaining volume. The remaining volume will be equal to cross section into depth. The cross section will be equal to what is the cross section area? 1 by L into h into L into L. So this is the remaining volume, and it is given as 1/3 of the volume is spilled out. So this is the volume which is remaining. Remaining volume is equal to 2/3 of the initial volume, which gives me value of H. So what is the value of H? So that 1/3 of the volume remains, it comes equal to 1/3, sorry, 2/3 of the volume remains, it comes to L by 3. So once I have this value L by 3 corresponding to 2/3 of the volume is still remaining in the container, I get the value of slope. And once I get the slope, I get the value of acceleration. Okay. Slope of the surface, I get the value of slope. If this is L by 3, this height is 2L by 3. So this 2L by 3 by L, I get the slope here, and the slope is equal to A by G. I get the value of acceleration at which 1/3 of the volume spills out. Okay, and this is something what you would have experienced. Most of you will observe every day. So if you have a tea cup of tea here, when you stir the cup of tea, we always find the level of tea or any liquid, which liquid we stir. The stir means we are giving an angular velocity omega. And in this case, we are taking ideal case here. Ideal case means every particle in the liquid is moving in a circular path, in a having a angular velocity of omega. So all of them having same angular velocity omega. In this case, so this at the center level of liquid will be lower. As we go further up, level will keep rising. It takes a shape kind of thing. This shape is paraboloid. And see this something what will happen if this was the initial level. So what we note over here. So what has happened? The liquid which was occupying this volume has moved over to the side. So there's a redistribution of volume. So some of the is, in a way, you can think of is something similar to centrifugal force. When you rotate any object, it tends to get pushed out. So the liquid, which is in the central region near the axis of rotation, has moved to the outer periphery, and it takes this shape. It becomes a paraboloid, and so there's a lowering of level, and we will not prove it here, and it's not. You don't have to prove that also. Whatever level it goes down here, similar level it goes up here. That is comes from the equation of the volume paraboloid property. So if we stir, then a center, it will go down by a certain height, and it will go by a certain height here, and these two are equal from initial level. So this is something in no proof, and this proof comes from the basically calculation of volume in 3 dimension, which is not our scope now. So in this case also, if we look at why does it take this shape, and understanding the shape is easy in a sense here. What I find if I take on the right hand side, the slope is positive. Why is the slope positive? Let me take a small piece of here. The slope here. So see, different point I will have different horizontal acceleration. So what is the acceleration? Acceleration will depend on distance from the center. See, when we calculate A here, what is the horizontal acceleration at a point which is at this distance from here? At a distance R. The horizontal acceleration here will be r omega square, but it will not be towards right, it will be towards left. So that is the horizontal acceleration, which is a function of r. So ax is equal to minus r omega square. That's the horizontal acceleration. And once I have the horizontal acceleration, I can write the equation. So that's why you notice here, as we go up, slope is increasing. So I understand why the slope increasing. Okay, let me think. What is slope tangent theta? So tangent theta is equal to minus of acceleration in horizontal direction divided by g. And so what is tangent theta at a distance r from here? So tangent theta at a distance r, what is the acceleration? Acceleration is minus r omega square by g. So which is equal to r omega square by g. So as we go further from the axis of rotation, slope will keep increasing, and that is AR. So I can substitute, I'm just using the similar expression slope here. In place of slope, earlier previous case I have written dh by dx. I am here, radial direction is important. So horizontal direction I have written dh by dr. Dh by dr is the slope at a distance r, and slope is equal to negative of horizontal acceleration divided by g here. Horizontal acceleration is minus r omega square. If I put these values, I get dh by dr equal to r omega square by g. And depending on which 2 points I can choose, I can find corresponding height difference. If I choose which 2 points, if I choose let's choose which 2 points you're interested. I want to find out what is the height difference between this point and this point. So when I'm calculating delta dh here, and if h is the vertical direction here, I will integrate this term dh is equal to r omega square by g into dr, from where to where? From r corresponding to 0 to r. That will give you h1 to h2. H1 to h2 difference is nothing but height here, delta h. So delta h comes equal to r square omega square by 2g at a distance r from the center. So any point at distance r from the center compared to the center point will be higher by r square omega square by 2g. And if I want to calculate what is the height at a distance capital R, which is radius of the container, we substitute r as a capital R. So some of you, you can start from here. Either you remember this part and arrive at this expression depending on what the question is, or you can just memorize this as a formula and try to understand where does the formula comes from. This formula gives you what is the height of a liquid surface at a distance r from the axis of rotation. And which point is taken as zero height, center is taken as zero height. So it gives you height of the liquid surface at a distance r from the center if all elements of the liquid are rotated with angular velocity omega. So this rotation, let me take one example of rotation. So this is something you have a horizontal tube. It is connected to three vertical narrow tubes. All cases, though it is drawn like this, you have to assume all cases are narrow tubes. So it is three-arm tube here, three vertical arms and connected by one horizontal arm. It is filled up to level height h, L. So this is L, this is L, this is L, all are filled up to the same level. Now it is rotated at an angular frequency omega about an axis passing through B. So which is the axis of rotation? This axis of rotation. So when we measure distance r, I will measure the distance r from here. So r is measured with reference to axis of rotation and angular frequency is omega. So what would happen? Will the level remain same? Similar to previous case also, what will happen? This level will start going down. And so liquid is being pushed from the region near to axis of rotation to region which is farther away. So here, unlike previous case, it is not a container here. There are three arms here. So what will happen if the liquid level goes down here and other two side liquid will go up? And because of basic volume has to remain same, whatever is a decrease in volume here, and these are two symmetrical. So if this goes down by length of tube H here, the other two have to rise by H by 2. Then only the volumes are equal. So decrease in volume has to be increase in volume or sum of increase in volume on two sides. So whatever is a decrease in height here, there has to be increase equal to half that height in other two columns here. The level and AC. So what is the question here? We need to find value of omega such that level of liquid in arm B becomes 0. So which level we have to go to? At this level. So this line becomes 0. It means the liquid level here drops by height L here, and other two side it has to rise by L by 2. So this one becomes L by 2, rise of L by 2 and rise of L by 2. So if I calculate, this is what has happened. So this will be the final shape it will look like. The final shape liquid will look like this. no liquid here. It has risen to what height here? Other height L by 2 from here. Now, how do I find value of omega? So there are 2 points at which I know what the heights are. Which are the 2 points I know? I know point at r is equal to 0. With respect to r is equal to 0, the height difference at r is equal to L. At r is equal to L, I know the height difference is equal to 3L by 2. So compared to this, the liquid level here, compared to this liquid level at a distance L is difference in level is equal to 3L by 2. So I'll use that equation. Difference in surface level over a radial distance of L is equal to 3L by 2. So what may I use my equation? Delta H over a distance r square omega square by 2g. So what is delta H? I'll substitute. Delta H is equal to difference in level, 3L by 2. And what is the distance r? R is equal to L square omega square by 2g. That gives you value of omega. So that's the angular velocity I need to rotate for this liquid level to become 0. Okay, that's the equation we obtain here. Okay, this question I'll skip. Okay, little. Some of you want to do, you can do it as optional question. Now coming to fluid dynamics. Fluid dynamics. In a steady flow of fluid in a tube, just imagine the liquid is flowing in a tube. Either it's a real tube or it could be a virtual tube also. How do you get a virtual tube? That's based on the streamline. Let's take the real tube. If it is flowing in a steady state, what we say here, the mass of fluid entering one end in unit time is equal to mass leaving at other end in unit time. So mass flow rate through this cross section is equal to mass flow rate out through this cross section. Why that has to be equal? If there's more mass entering the same volume remaining same, if mass increases, what will happen? The density of the liquid has to change here, which is not a steady state. So just by the fact that volume within the two cross section remain constant and density remain constant, it gives to this condition mass flow rate entering through cross section here has to be equal to mass flow rate out. So we have done volume flow rate is area cross section into velocity. Mass flow rate is density into area cross section into velocity. So these two values must be equal in a steady state. So when the density here is not changing, which is anyway case, and if a density is constant, even in unsteady state also this has to hold true. Because here the density also cannot change, volume cannot change. So whatever volume has to enter, same volume has to go out. For incompressible fluid, the change in volume with change in pressure is negligible or density is constant. So A1 V1 is equal to A2 V2 is very simple continuity equation. This is called equation of continuity. And we can call this term as volume flow rate through cross section A1 and A2. And based on this is equation of continuity, and then you further derive what we call as Bernoulli's equation. Bernoulli's equation comes from basically application of Newton's law. So here when the pressure is acting and there's a small displacement. So when we have there's some impulse acting here, there's some impulse acting here. We'll not go into derivation, but Bernoulli's equation for non-viscous, because we go to derivation that takes 15-20 minutes. So Bernoulli's equation is valid for non-viscous. So basically what it assumes, there is no loss of energy due to friction. So viscosity will come a little later, but fluid is not non-viscous. There's no friction between layers of fluid. It is incompressible, and which is mostly true. Non-rotational means when the liquid is flowing in a streamlined path. You kind of see sometimes the liquid flows kind of whirl. Whirl means it is coming back also. So that becomes rotational. This is not rotational and streamlined flow. So streamlined flow means if all liquid particles which are passing through the particular point, they'll always follow the same path. It will follow, so they'll follow take path. So it's just like a path, all liquid particles one by one, which is passing the point, all takes the same path. They keep moving along the same path. So if I inject a dye here at one particular point, if I keep injecting color dye here, I will see a kind of strand running through along the straight line. It will not mix up anywhere here and there. So no turbulence here. So when we have this kind of equation, what we find, we get expression like this. And you can think of this expression as conservation of energy here. See, those two terms we are know, but since we are talking about continuous mass flow, so when this continuous flow is there, what is the mass I should take here? So here, what is taken? Mass is taken. Here we are calculating energy per unit volume. So we are taking one unit volume. What is the energy? What is the energy per unit volume here? And what is the energy per unit volume here? So what is energy per unit volume here? So here we calculate energy, kinetic energy. I would have written as 1 by 2 mv square. But 1 by 2 mv square, if I divide by volume, it becomes density, mass by volume. So those are expression. This is kinetic energy per unit volume. This potential energy, depending on which point I choose as my reference level. If for gravitational potential, I take this as reference. Height of the liquid particles from the reference level, mgh divided by its volume. So mgh divided by volume, it becomes rho. So 1 by 2 rho v square, kinetic energy. This is potential energy due to some reference. We have one more term coming because of pressure. This is a new term, which is pressure energy. So in terms of dimension, energy per unit volume is equal to pressure at that point, and this is equal to constant. So, or you can say you could have written as rho 1 v1 square plus rho 2 GHNL 1 2. So basically, it means constant across any two cross section. So Bernoulli's theorem, moment you think of Bernoulli's theorem, is nothing but similar to conservation of energy. There's one additional term, and additional term is pressure energy, and all energy terms are expressed in terms of energy per unit volume. That's why I take this kind of expression. So let's look at what are the three forms of energy per unit volume. Okay. So let's see some applications of the same. So in this case, this is kind of syringe where you would have seen, and you can see in many shape. But this is something. So when we inject injection also, what is injection composed of? It has a kind of cylinder which is slightly larger radius, followed by a needle. So needle has a very small radius. Okay, so this is something when we from here we apply a force here, and it pushes the injectable fluid into the body of human, and you can have several. So basically, it is something similar to that. So liquid is being pushed out of a tube by pressing a piston. Area of cross-section piston is given. So this area is given A. A is equal to given as 1 centimeter square. And that of the tube of the outlet, this area. So this area also is given. Area is equal to 20 mm square. Okay. And if the piston is being pushed at the speed of 2 centimeter per second. So this piston is moving at the speed of 2 centimeter per second. What is the speed of outgoing liquid? So we have to find what is the value of V here. So this piston is being pushed here. So basically, if all the liquid molecules which are right next to the piston are moving at the speed of 2 centimeter per second, since the total volume has to remain same, all liquid particles within this cylindrical part also will move with the velocity of 2 centimeter per second. So it is equivalent to continuity equation. This one cross section A1 here. It has certain velocity V1 here. The liquid is flowing out from cross section A2 with the velocity V2. So A1 V1 is equal to A2 V2 will give me the velocity, what is velocity with which it will move out from here. And if there's no friction anywhere here, if there's no loss of energy, the kinetic energy acquired here by the liquid which is flowing out, I can calculate what is the kinetic energy of liquid flowing out in a unit time. That kinetic energy is coming because of work being done on the piston. This force also. So if we assume there's no loss of energy, what force is needed also can be calculated in those terms. I can calculate force equal to rate of change of momentum. So rate of change of momentum easily we can calculate. dm by dt into v will become rate of change of momentum, and force also can be calculated. This is basically simple continuity equation. No friction anywhere. Work done by force is equal to kinetic energy of liquid squirting out of the syringe here. Okay. What are the other applications of Bernoulli? See, in fact, very commonly we talk about, aircraft. Aircraft also, some of you might have noticed also, the aircraft takeoff, landing, all those things are basically controlled by the wings, what we see there. And for the takeoff, what has to happen? The aircraft has to move, it has to have certain high speed, then only it can take off. When it acquires a high speed, actually what happens as aircraft travels at a high speed, its relative velocity with air becomes high. So what really matters is the relative velocity between surrounding air and the wing. And when aircraft is flying at a particular altitude, it means the net force acting on the aircraft has to be zero. If net force is acting zero, what is making the net force zero? The downward force acting is gravitational force, weight is always acting. And even at that height of 5 kilometers also, G value does not change much. So its weight remains same, but it is kept at that height because of contact force with the air. So upper part of the wing also has contact force, lower part also has the contact force. So upper part is exerting pressure and force, and lower part also there's a pressure and the force. Here the pressure only leads to the force. And if aircraft is flying and so net force, if we take net of the two, the net of the two has to be acting in the upward direction. So let's understand how does that happen. And this happens by manipulating the speed of air particles which are traveling above the wing and which are traveling below the wing. So here they have certain velocity. So what it shows here, this is designed and angled in a such a way that air molecules which are in this frame of reference coming with certain energy, this air molecules, some of them go up and some of them go down. More flow is more directed in the upper side of this. So this side more flow is going. See, in this case, what is given? The velocity of air very close to the wing on the upper side is root 2v, and velocity of air in contact with the wing on the lower side is v. So when this kinetic energy is greater, if kinetic energy is more, by applying Bernoulli's law, if one form of energy is greater, some other form has to be smaller. So here, if kinetic energy is greater, the pressure energy is smaller. So pressure on the upper part of the wing is lesser compared to pressure part on the lower part of the wing. And this pressure being higher, the difference in pressure gives it upward, it gives a lift kind of thing. So when we look at the Bernoulli's equation, lower velocity indicates higher pressure. And so when we want aircraft to keep flying, here we want lower velocity, higher pressure. So can we calculate this expression? This is a simple expression, 1 by 2 rho v square P1. And where's the P1 here? P1 is on the lower end. This I am taking as a lower as P1 and upper side is P2. So we write this expression, and what is the net force acting on the wing? Net force acting on the wing will be P1 minus P2 into area. That's the net force acting. So can we calculate P1 minus P2 here? P1 minus P2 easily can be calculated, and P1 minus P2 into area becomes the dynamic lift on the wings. So again, to repeat, this is just based on total energy remaining constant. If one energy form of energy, so I'm just writing height is no difference between the two. So we write energy of air particles which are above the wing and which are on the lower side of the wing. And most cases, actually, it may not be as simple as this, but as far as examination goes, this is the simplest view we will take. So any surface, if there's a difference in velocity, it will create pressure difference, it will create net force. And something this happens in case of hurricane also. So delta P, this becomes delta P into area, that becomes your dynamic lift. Dynamic lift is delta P into area. Okay, and one more common example of application of Bernoulli's equation or Bernoulli's theorem is velocity of F flux here. So velocity of F flux, let me see this. Let's see what we do here, velocity of F flux. Most cases we take cross section, the velocity of F flux. See here also similar to serene. If I take a cross section just below the water level here, this is one cross section. And this is the second cross section just outside the nozzle. The point B is just outside the nozzle and this another surface here. And this I take section 1. And if I take this as section 2, we can write a Bernoulli's equation between these two. But when we write this Bernoulli's equation, I am writing 1 by 2 rho v1 square. Rho v1 square is velocity at this section and v2 is velocity at this point. But a1 v1 is equal to a2 v2. So here what we say here, if we take this cross section total area A and AB, this is in case of a vessel with a small hole, cross-section area AA is much greater more than AB. If that is much more than AB, then if I write equation of continuity, area of A into V1 has to be equal to area of B into V2. If this is very large, V1 will be very small compared to V2. So velocity at which the liquid particles will be moving downwards on the surface or near to the surface, this velocity will be much lower than velocity of the liquid particles which are flowing out. So when we are comparing, when we come and again when we to calculate kinetic energy, you square it. So this term becomes negligible. So majority of the cases, though the right equation should have V1 term as well as V2 term, but most cases where this cross section, this vessel is large compared to size of the opening, we ignore the term V1 here. So when this is one, we could have written this equation. So when we write this equation here, what are the terms we write here? So if I write here, let me write the equation here. Pressure here at 1 is P naught. That's what he written. Kinetic term 1 by 2 rho n square we have ignored here. And if I take this as a reference level, which point is reference level? Nozzle as a reference level at rho gh, height from above the nozzle level. That becomes equal to, sorry, I missed this term P naught here. This P naught has to be added here. So this equal to 1 by 2 rho v square plus P naught. And why we have taken a point, liquid point here just outside the nozzle. So as soon as it comes out of the vessel, it is exposed to the atmosphere. It will have same pressure as the atmospheric pressure. That's why we take the second point just outside the nozzle. And when we equate this one very easily, we can arrive the equation soon after opening. So soon after opening, it becomes equal to, okay, so this is the expression we arrive at. And from here, we can easily find what is V equal to. V is equal to root 2 gh. That's the velocity of F flux if we ignore kinetic energy at the surface. And this, very surprisingly, the whatever liquid volume what it comes out is equal to same rho gh. We have seen that it is equivalent to if a liquid particle is made to fall and any object fall from this height edge, it will acquire the same velocity. So when it moves from here to here, potential energy, see, pressure energy has not changed. If pressure and energy not changed, only form of energy which has changed is potential energy. Pressure energy has remained unchanged. Here also atmospheric pressure, here also atmospheric pressure. But this question I can interpret in slightly different way. This is one way of equating forming equation based on Bernoulli. Let's start second way. Let's try this way, and I think this is something is more easier to solve in many cases. Let's first assume that this opening was closed. When this opening was closed, the liquid particle was inside the vessel at this point and at this point. So when it, and after I open this one, this particle start flowing and it comes out of the hole here. So this particle before the hole was open, and this is after the hole is open. So during this period, what has happened? Both cases, the energy has not changed. So whatever energy it was there in one form, it has been transferred to some other form. Which energy has been transferred here? Here it had a pressure energy. Here it had a pressure energy equal to phi, right? So what has happened soon after opening? So before opening, it had a pressure only P. This reference level. It only had a pressure energy PP, nothing else other than that. Your kinetic energy is 0, and I'm choosing this as a reference level. So before opening, the energy per unit volume was equal to pressure at P. After opening, it will start flowing with velocity V, and atmospheric pressure is P naught. So what is energy soon after opening? P naught plus 1 by 2 rho V square. And these two are equal. So when I equate those two things, what you get here? PP minus P naught is equal to 1 by 2 rho V square. Do we understand what is PP pressure at P minus atmospheric pressure? Is nothing but gauge pressure. So gauge pressure gets converted into kinetic energy. That is simplest way you can think of. So whenever, how do we arrive at kinetic energy? Whenever this hole is open to atmosphere, we equate this energy to energy of the liquid particle which was at rest before the hole was opened. So before hole was opened, if we take this as a reference level, only form of energy it had was in form of pressure energy. And since outside also because atmospheric pressure, I can take the gauge pressure energy has got converted into kinetic energy. So gauge just outside hole where pressure is atmospheric equal to gauge pressure at the same level. Okay. so that we can look at some applications later on. And after this, what happens after this? If you open this here, we can all have seen this kind of it falls like this, and the trajectory here of the liquid particle is same as trajectory of particle moving under gravity. Because here also all liquid particles are moving under gravity, and this is a parabolic trajectory. So after it is open, it follows a trajectory path. If the tube here is horizontal, it becomes a horizontal projectile kind of motion. So horizontal projectile motion, if I have to calculate range here, how would I calculate range? Range in case of horizontal projectile, how do we calculate range here? Range is equal to uh, time of flight into horizontal velocity. This height is equal to capital H minus small h. Small h is the depth of hole from the liquid surface level. H is H is the height of the liquid surface from the ground where water is falling. So this is time of flight will be equal to 2 root h minus h by g into v. That becomes range here. If I put v value is equal to root 2 gh, this becomes my range. 2 comes out. So range is equal to twice of what is this term here? H minus twice of what? One is height of liquid level from the opening, and second term is height of the ground below the opening. So H minus H is height of the nozzle or hole above ground level, and this H is height of the liquid level above the hole. So product of these two product is equal to twice of this into this is equal to my range. And this also very simple formula. I don't think you need to memorize of this. So what we understand here, it is product. So suppose this height is equal to 4 meter. So if I have a tank of height of 4 meter, if I drill a hole at h is equal to 1 meter, this will become 3 meter. It will have particular range. But if I make a hole not at 1 meter, if I make a hole at 3 meter depth, then this will become 1 meter. Both cases, these two will interchange, range will remain same. So when we interchange h minus h and h, the range will remain the same. So if we make a hole from here, height of 1 meter from the top, total height being 4 meter. Other one, I make a hole 1 meter from the ground level. Both cases here it will fall like this. And even this also will fall like this. Both will hit the ground at the same point. And when is the range maximum? Range is maximum when hole is made at the midpoint, when two are equal. So very easily you can calculate. So that is what happens in case of a velocity of F flux when the hole is made from a liquid tank. So let's take some applications of the same here. So tank is filled up to height of 2h. There's a liquid tank here, and is placed on a platform of height h here, and that's the ground level here. Distance y. So what is asked here? What is the distance y from the ground where a small hole should be made in the tank so that range is maximum? So we need to calculate where should a hole be punched in the tank, and that distance has to be measured from the ground. What has to be the value of y so that the range is maximum? See, the very simple. See, there are three things are relevant here. This one is water level. And this is ground level, because the range calculation, it has to fall onto the ground. So this is the next point is my ground level. What happened? Okay. So this is ground level. And this is hole level. So when is the range maximum? When water level to hole, this and these two are equal. So hole to water level is equal to hole to ground. So here total is 3h. So it means this has to bisect these two. So this y has to be equal to 3h by 2. That's all. Hole should be the midpoint of water level and ground level. And if you have to calculate range, calculation of range is simple. The formula is also there, but very easily we can arrive at that value. Velocity will be equal to root 2 into this height here. And the range, very easy formula, horizontal projectile. Now let's look at some cases where it is not one liquid, and that becomes a little more interesting. So you have two immiscible liquids. So you have a vessel. You can have several liquids are immiscible. So and typically it will remain immiscible if a lower one has a higher density. So they will not. This will not tend to sink in. So this one has a density of 2 rho, and upper liquid has density of rho. They are filled in the vessel as shown, and two small holes are punched at midpoints here. This is at h by 2, and of course punched at a depth from the surface. This becomes 3h by 2. So when we punch a hole from this top hole, this liquid will start flowing out. From this bottom hole, this liquid of density 2 rho will start flowing out. Let's say this velocity is v1 and this velocity is v2. How do we calculate those velocities? V1 is very straightforward. It is same liquid, and this height is equal to h by 2. So velocity is equal to root 2g into the height of liquid level from the hole. It becomes 2g into h by 2. So that is V1 is straightforward. But when we come to second liquid here I cannot take that height here. There are two different liquids here and the densities are changing. So in such case, it's much easier to calculate what is the pressure, gauge pressure at this point, which I was talking last time. So, and this gauge pressure becomes equal to my kinetic energy per unit volume. So can I calculate? So what I have in mind, so again to repeat this point, gauge pressure at P will become equal to 1 by 2 into density of the liquid, which is equal to 2 rho into V2 square. So only thing I need is pressure at this point, that to gauge pressure. So gauge pressure, I'll take the pressure at this surface, atmospheric pressure is 0. So pressure here is equal to, from here to here, increase in pressure is rho gh. So this is a term, rho gh. Then from here to here, further increase in pressure, this height is h by 2. But density is 2 rho into g into h by 2. So the pressure becomes equal to 2 rho gh. So this is the pressure term here. Now what I need to pressure energy difference is equal to kinetic energy. The pressure energy difference, since I'm taking gauge pressure, outside pressure energy becomes 0. So this term, the gauge pressure, I equate to 1 by 2 into density of the liquid which is flowing out into V2 square. I get this velocity as rho 2 gh. So very simple way to calculate that one. Okay. Other variations of the same. So because this is one of the important point, velocity of F flux and questions related to velocity of F flux. We have a cylindrical vessel which contains liquid of density rho up to certain height h here. And liquid is closed by a piston of mass m. So there's a piston and this is not a massless piston, its mass is m. And cross section is area is A, and the cross section area is same as the area of cross section of the vessel. And there's this small hole at the bottom of the vessel, and the liquid flows out velocity v. We need to find out what is the speed v with which the liquid comes out of the hole. And again, moment is given like this, we could still apply Bernoulli's theorem, but that becomes a little circuitous. Again, how would I solve this question? All I need is the gauge pressure at this point. Can I calculate gauge pressure at this point? So gauge pressure, first I need to calculate what is the gauge pressure just below the piston, and then I can add that change in pressure due to depth h here. So this also, again, let me calculate top hole. Sorry, what happened? Okay. So this is scratch it. Gauge pressure just inside the hole, assuming closed, it will be equal to rho gh, but pressure here will be equal to mg by a. I think we have done it earlier also. So excess pressure, see net force acting on the piston due to differential liquid pressure. Outside pressure is P naught, here P naught plus delta P. So if I take gauge pressure, outside gauge pressure is 0. Inside gauge pressure, I am calculating. So gauge pressure will be equal to mg by area of cross section. So this is the pressure at this point here. And this pressure I equate to kinetic energy per unit volume as it flows out. It will be 1 by 2, density is V into V square. That will be the value here. Okay. So that's the speed at which liquid flows out. Very simple. So I am just calculating pressure near the hole. I am calculating pressure, assuming this initially it was closed. When it's closed, this pressure energy gets converted into kinetic energy. That kind of simple logic we use to calculate the value. So pressure difference is equal to kinetic energy. The expression we write, and we get the value of V. Okay. So in this case, again, figure looks very similar and should look familiar here. This light cylindrical vessel. So vessel has negligible mass. So this is a vessel here, which is light vessel, negligible mass. And this vessel is kept on a horizontal surface, base area is A, and whole of cross section area A. So this area of cross section of hole is much smaller than area of cross section of the vessel here. And what should be the minimum coefficient of friction necessary to prevent the sliding of vessel due to emerging liquid? So it is kept on a surface here, and it says if it does not slide, we need certain value of coefficient of friction, then only it will not slide. Otherwise, it would slide. So first question comes as soon as I open the hole. It makes common sense if the whole thing was kept on a really smooth surface. As soon as the liquid start flowing out, it is some we have come across this kind of thing before. It will exert a force on the remaining tank in the backward direction. And why is that force? We have seen in case of fuel injection, ejection in case of rocket also. It is similar to throwing a ball in particular direction. It's a variable mass system. Force exerted, so this liquid which is flowing out is exerting force on the rest of the mass here, or rest of the mass have exerted this force on the liquid. The rest of the mass has exerted the force because the pressure here, the pressure was there which has changed. So you can understand where from the force on the liquid is coming. This is coming in form of force which is pushing it out, and so liquid is exerting on for liquid inside the container is exerting a force on the liquid going out in the rightward direction. This will exert a force in the leftward direction. How much that force is? Force is dm by dt into velocity. This is mass flow rate. Mass flow rate is, we have seen earlier also, is rho into area of cross section into velocity, and one more velocity, it becomes rho a v square. Thus the force exerted by the liquid at flux. So this whole container will behave as if somebody is pushing it with this force. If this is the force someone is pushing it, it has to be resisted by friction force. And whenever we have calculated minimum coefficient of friction, it is a limiting state of friction. Minimum coefficient of friction is a limiting state. Frictional force has to be equal to maximum frictional force, which is equal to mu times normal reaction, mu times mg. And what is m here? M is the mass of container plus mass of the liquid, mass of the whole system. And since the container is given as a light container, this m is the mass of the liquid contained in this volume. And this mass of liquid also can easily calculate density into volume, density to h into a. So this m is equal to rho into h into a. So we write this expression, rho a square is equal to this expression. Okay, so I know this is something I think I typed wrongly. So this mu mg is equal to rho a square. M value you can easily find, mass of the liquid plus container is equal to rho into a into h. So this gets you value of mu from here. So this question also should understand, it may come in different form. What is important point to understand? So whenever the liquid flux goes out from the tank, it exerts, it's a variable mass kind of system, it will exert a force on the remaining container, and that force is equal to dm by dt into v. It means container also is exerting a force which is like this, and that force comes because of differential pressure. Just imagine the liquid here, this liquid particle here, remaining liquid inside will exert a pressure which is equal to P naught plus rho gh, whereas other side is only P naught. There's a differential pressure, that's why it is exerting a force. So this is a force which is causing this kind of motion. Right, so this is what about fluid dynamics, about velocity of a flux. So right now we'll stop here. We'll take 10 minutes break, and then we continue after this.